Okay, let's unpack this. We are diving deep today into what feels like, well, a really dramatic shift in our skies. It's like a season of unprecedented cosmic activity.
It really is.
We're tracking what some observers are calling a flock of comets, descending upon the inner solar system. But the true star of this show, I think, the one causing all the confusion and excitement, is this enigmatic interstellar traveler known as 3I ATLAS.
It truly is a remarkable time for watching the skies. And you hit on the right point. 3I ATLAS is, well, throwing curveballs, big ones.
How so?
When we analyze its chemical fingerprint, what it's actually made of as it heats up, we're finding this bewildering cocktail of outgassing materials.
Okay.
You've got carbon monoxide, carbon dioxide, substantial amount of water, which is maybe expected.
Right. Standard comet stuff?
Sort of. But then, most surprisingly, isolated atoms of nickel. Just nickel floating free.
Nickel, that sounds odd.
It's very odd. This object isn't just a comet. It feels more like a messenger, maybe, from another star system entirely. It's carrying secrets about the universe's history, secrets we are, frankly, desperate to decode.
And that urgency, that desperation almost inevitably leads to, well, sensationalism, doesn't it?
Oh, absolutely. The headlines.
Yeah,
we're seeing headlines screaming about a coordinated arrival or even a fleet accompanying 3I ATLAS. So our mission right now, I think, is to cut through that noise. We need to figure out, is this influx of objects, this flock, is it a sign of some grand coordinated pattern? Or is it simply a grand astronomical coincidence, maybe amplified because our detection tech is just better now?
That's the crucial question. And the initial data, well, it seems pretty clear on one thing. We really need to dismiss the idea of a coordinated fleet.
Okay, so no invasion fleet. That's good news.
Right. While it's certainly a busy season up there, no doubt about it, most of the passing objects we're seeing are just, run-of-the-mill, homegrown neighborhood asteroids and comets. Stuff from our own backyard. Our usual cosmic neighbors.
Exactly. They're definitely not traveling together with 3I ATLAS. If you look at the kinematics, that's their individual movements, speeds, directions.
The trajectories.
Precisely. They're arriving from completely different angles on totally disparate trajectories. They belong to our local solar system's vast collection of icy bodies and rocks. They are not part of some grand entourage accompanying 3I ATLAS. It's a fascinating time, a really interesting cometary season, yes, but it's not an invasion.
Though that fascination, that pull towards the cosmos, it really is the driver behind so many of my own long-term projects, actually. We talk about the abstract beauty of astronomy here all the time, but I've been trying to anchor that abstract idea in something real, something tangible. I'm currently consumed, maybe that's the right word, by the purchase and initial development of land for a new kind of educational facility.
The school project.
Yeah.
The dream is starting to become reality, isn't it? I know how meticulously you're planning that initial infrastructure.
Yeah, meticulous is one word for it. That's the idea, anyway. And while I've been deep in spreadsheets, figuring out infrastructure costs and surveying, wrestling with initial power lines, water lines, all that groundwork.
The unglamorous stuff.
Exactly. But one criterion for the land itself was absolutely non-negotiable. It had to have high ground.
For the observatory.
Precisely. There is this prominent ridge on the property, it just sort of calls out. And in my mind's eye, I am already sketching out the details of a magnificent observatory perched right on top.
That sounds incredible.
Because when we talk about these massive celestial visitors, these comets like 3I ATLAS or near-Earth asteroids whipping past, I want to be able to just walk up that ridge and view them in real time, see them moving against the stars. That connection, I think, makes the science immediate, tangible, especially for future learners.
That tangible connection is vital. It makes all the difference. Meanwhile, back here in the data streams, the scientific consensus is definitely solidifying. 3I ATLAS is a comet, yes, but it is deeply anomalous. It's weird.
And we really need to be crystal clear about that distinction for you listening, because up until very recently, literally 100% of the comets where we had detailed observations, they were homegrown.
Right.
Born from the same primordial solar nebula, that swirling cloud of gas and dust that created our own sun and planets.
Correct. Standard origin story for everything we knew. But these interstellar objects, first oumuamua, then 2I Borisov, and now this one, 3I ATLAS, they had their genesis in the protoplanetary disks surrounding other suns. Completely different star systems.
Wow, so they're cosmic refugees in a way.
You could say that. They were likely ejected from their home systems billions of years ago, maybe through planetary migrations or gravitational interactions we can only guess at. They are fundamentally foreign, alien in the literal sense.
Which means?
It means that compared to the objects we grew up with, the comets from our own Oort cloud or Kuiper belt, these visitors are chemically and structurally unique. They carry the signature of their birth environment. They are interlopers, true outsiders. And that's precisely why the data we are getting from ATLAs is so, well, shocking in some ways.
That context, foreign bodies versus homegrown ones, it feels vital as we discuss what seems like this influx. The sheer number of active objects visible right now makes me think about what scientists call the clumpy nature of cosmic encounters. Is that related?
It is very much so. And this takes us back actually to the early 1980s. Serious scientific thinking about catastrophic impact events really gained traction with those bombshell papers by the Alvarez team.
Dinosaur killers.
Exactly. They proposed a celestial mechanism, a massive comet or asteroid impact, to explain the mass extinction event at the end of the Mesozoic era, the KPG boundary. That paper basically reignited global interest in just how profoundly these objects, comets, and asteroids influence Earth's history and maybe its future.
What I always found so elegant about this whole field of study is how it organizes our cosmic address, you know? We have the inner solar system, the rocky planets like us, inside the main asteroid belt, and then there's this massive cometary zone that stretches way, way out beyond Neptune.
And we typically break that huge cometary zone into its two key reservoirs, its main sources. First, you have the Kuiper belt. That's a huge disk, kind of like the asteroid belt, but much bigger and icier, starting just beyond Neptune's orbit.
Okay.
The comets originating there are generally the short period ones. They tend to orbit the sun in less than 200 years, and they usually arrive at a relatively low inclination, sort of close to the flat plane where the planets orbit, the ecliptic.
And then way out beyond that, the true reservoir of these long-shot visitors, the Oort cloud.
The Oort cloud is, well, it's almost unimaginably vast and distant. It's thought to be a giant spherical shell of icy debris completely enveloping our entire solar system, maybe stretching almost halfway to the nearest star.
Wow, a sphere.
A huge sphere. And these are the source of the long-period comets. They can take thousands, maybe even millions of years to complete just one orbit around the sun. And because they come from this spherical shell, they can arrive from virtually any direction imaginable, often at very high inclinations, plunging down from above or up from below the ecliptic plane.
But the core revelation here, the really important part for understanding this busy season, is that the delivery mechanism, how these icy chunks get nudged from those distant reservoirs and sent careening into the inner solar system, it's not smooth. It's not steady like a conveyor belt.
Exactly. It is clumpy. I think your analogy of traffic patterns on a highway is actually pretty good. Kinematic.
Right. Like sometimes you hit rush hour, sometimes it's clear.
That's the key concept. These clumps, these rush hours, are often driven by massive external gravitational perturbations. You have to think about the larger structure of our galaxy, the Milky Way.
Okay, bigger forces at play.
Much bigger. As our entire solar system orbits the galactic center, it periodically passes through denser patches of interstellar matter, giant molecular clouds. Or maybe it feels the gravitational tug of nearby passing stars out in the galactic disk.
So it's not just Jupiter or Saturn playing gravitational billiards nearby. It's these huge external galactic forces disrupting the Oort cloud's delicate balance way out there.
Precisely. Those galactic tides, or a close-ish stellar encounter billions of miles away, can momentarily disturb millions, maybe billions, of these loosely held Oort cloud objects simultaneously. It can shake the tree, so to speak.
And send a whole bunch of them tumbling inwards.
Throwing vast numbers of them inward, many on trajectories that bring them into the inner solar system. That's why we see this clustering effect. We might be watching that vivid clustering right now, actually demonstrating that the delivery mechanism is fundamentally non-uniform, it's episodic,
And this clustering, this clumpiness, leads us directly to the significance of what the British School of Astronomers called comet epochs, or comet showers. Why does that clustering actually matter to us down here on Earth?
It matters because of the inherent fragility of the comets themselves.
They fall apart easily.
Very easily, relatively speaking. When multiple large comets are forced into the inner solar system over a relatively short astronomical timescale, we're talking maybe thousands or tens of thousands of years, they just don't handle the intense heat or the sun's powerful gravity very well. They are, at their core, fragile structures of ice, dust, and loosely bound rock.
Okay.
They tend to break up. They fragment under the intense thermal stresses from sunlight and the gravitational tides from the sun and planets.
And that drastically increases the potential for Earth to encounter their debris streams and fragments, right?
Yeah, that's the potential danger, yes. A single large comet hitting Earth is obviously a major threat, but a comet shower, a period where many large comets are fragmenting in the inner solar system, drastically increases the statistical probability of Earth encountering something either as a significant fragment or a dense debris stream. Think meteor storms, but potentially much worse.
So the current busy period isn't just a spectacle.
It underscores the relevance. It's not just a pretty show. It's a moment when the cosmic shooting gallery feels, let's say, a little more active than usual.
That inherent fragility brings us right back to 3I ATLAS, which is proving to be incredibly active and, as you said, highly unusual. Let's dive into its core mystery, this nickel and water anomaly you mentioned.
Right. When the Very Large Telescope, the VLT in Chile, first tracked its outgassing activity really carefully, the chemical signature immediately jumped out as being strange.
How so?
They found these pure, isolated nickel atoms in the coma, the gas cloud around the nucleus. Now, cosmically speaking, nickel is what we call a siderophile, an iron-loving element.
Meaning it usually hangs out with iron.
Exactly. In almost all known cosmic alloys, meteorites, planetary cores, nickel is found bonded tightly to iron. They're like chemical buddies.
So, seeing pure nickel vapor being released, why is that such a game changer? Why the fuss?
Because the immediate, profound question that pops into every astrochemist's head is, where is the iron? Why is this nickel completely isolated from its usual partner? If 3I ATLAS were just a fragment of a typical metallic asteroid, or even a rocky body from our solar system, the iron should absolutely be there too, outgassing alongside it or locked in the dust.
So the absence of iron is the key clue.
The absence of iron alongside the nickel suggested that the nickel wasn't part of a standard metal alloy. It had to be bound up in something else entirely, something far more volatile, something that could release the nickel easily as the comet warmed up.
And that profound anomaly that where's the iron question naturally led to a pretty wide spectrum of theories, I imagine.
It certainly did, and we have to address the outliers, the more exotic suggestions. Like the idea, proposed in some corners of the community, that the nickel could actually be exhaust from some kind of alien propulsion system, a space engine, if you will. We have to put that on the table because it was proposed, however unlikely most scientists think it is.
Right, acknowledge the speculation, but what's the more mainstream, conventional explanation?
The more conventional and frankly much more likely chemical explanation points toward a specific, naturally occurring, though perhaps rare, compound. Nickel carbonyl.
Nickel carbonyl. Okay, help us visualize that. What is it chemically?
It's a molecule where a single nickel atom, Ni, is surrounded by 4 molecules of carbon monoxide, CO, so NiCO4, and crucially, it's known to be highly volatile.
Meaning it turns into a gas very easily.
Very easily at surprisingly low temperatures. And its specific sublimation properties, the temperature at which it goes from solid ice directly to gas, provide a really elegant natural explanation for the strange sequence of gas release we observed.
Okay, let's break down that chemistry slowly then, because these sublimation temperatures, as you said, they seem to be the key to understanding the timing of these outgassing events as the comet gets closer to the sun and warms up.
Absolutely. It's all about the sequence. Remember, sublimation is when a solid, like ice, turns directly into a gas, skipping the liquid phase. We track these critical temperatures in Kelvin, which starts at absolute 0.
Right. colder is lower Kelvin.
Exactly. So if we start with the most volatile component we detected, the easiest one to turn into gas, that was carbon monoxide, CO. It sublimates when it's extremely cold, somewhere around 25 to 35 Kelvin.
Which is incredibly cold in Fahrenheit.
That's approximately minus 414 degrees Fahrenheit. Way, way colder than deep space needs to be. So CO is likely the very first gas to start firing off as the comet begins its long, slow warming process, probably when it's still very far out in the solar system.
Okay, so CO fires off first, way out in the cold. What comes next in the sequence? And crucially, how does the nickel fit in?
Okay, next up, as the comet gets a bit closer and warms slightly, we hit the sublimation range for nickel carbonyl. It goes from solid to gas between about 74 and 82 Kelvin.
And that translates to?
Roughly minus 315 degrees Fahrenheit. Still incredibly cold, but significantly warmer than the CO threshold. Now, here's the critical part. Once that nickel carbonyl turns into a gas, the molecule itself is chemically unstable when it's exposed to the vacuum of space and the sun's ultraviolet radiation.
So it breaks apart.
Instantly. It rapidly decomposes, breaking down and releasing those isolated pure nickel atoms that the VLT detected.
Got it. So the nickel was never just floating around bare in the ice. It was hidden inside this highly volatile nickel carbonyl compound. And the compound's instability explains why we see pure nickel vapor.
Precisely. The nickel release is a secondary effect of the nickel carbonyl sublimation and breakdown, and the timing of this nickel release is beautifully corroborated, almost perfectly matched, by the other key volatile compounds we detected.
Like what?
Well, carbon dioxide, CO2, you know it as dry ice, begins to sublimate right around 80 or 90 Kelvin.
Yeah.
Just slightly warmer than or overlapping with the nickel carbonyl range.
Okay, so they come off at roughly the same time.
Pretty much. And we also detected hydrogen cyanide, HCN, which astronomers often just call cyanogen in this context. That sublimates near 79 Kelvin.
Wow, so it's really tightly clustered.
It is. You have the nickel carbonyl sublimating around 74, 82K, the cyanogen around 79K, and the CO2 starting around 80, 90K. They all essentially pop off almost simultaneously as the comet crosses that critical 80 Kelvin temperature threshold on its journey inwards.
That's amazing chemical synchronicity.
It really is. It's a perfect sequence predicted by known chemistry. The whole pattern of outgassing aligns perfectly with these rising temperature thresholds as 3I ATLAS gets closer and closer to the sun. It moves from CO firing off first, way out, then this nickel carbonyl cyan of CO2 cluster kicking in almost together, and then finally, much closer to the sun, the water ice, H2O, starts to sublimate.
And water is the warmest.
Water is the least volatile of these common ices. It only really starts sublimating significantly around 150 to 170 Kelvin. That's about minus 150 degrees Fahrenheit. Much warmer, relatively speaking. So the entire process, this observed sequence, points very strongly towards a natural chemical explanation rooted in the comet's exotic composition, likely reflecting the unique conditions of its parent star system.
That meticulous chemical detective work is fascinating, and it brings us to sort of the bigger picture, the anatomy of an alien comet and this related mystery of its incredible brightness puzzle. We're essentially watching 3I ATLAS wake up from billions of years of cosmic hibernation.
That's a great way to put it. For potentially billions of years, it existed in the profound cold of interstellar space, probably hovering just a few degrees above absolute zero, a true galactic ghost. Now, as it enters our sun's domain, our neighborhood, the warmth starts that sublimation process we just discussed. The volatile ices start turning to gas, creating the coma and tail.
Yeah.
The challenge is, its window for close-up study, for us to really get a good look, is agonizingly brief before it speeds right back out of our solar system, likely forever.
And those early VLT observations, they showed it was active unusually early, didn't they? You mentioned VLT, of course, the Very Large Telescope in Chile, and we should clarify, heliocentric distance just means its distance from the sun, usually measured in astronomical units, or AU, where 1 AU is the Earth-Sun distance.
Correct. And the comet was showing definite signs of mild activity, a faint coma, even way out at 6 AU.
6 times Earth's distance from the sun, that's way out there beyond Jupiter's orbit. That is unusually early for a comet to turn on.
It is. And this high level of activity, particularly as it got closer, led to that striking visual anomaly, the thing some people started calling an anti-tail.
An anti-tail, what does that look like?
Well, normally a comet's main tail, the ion tail and the dust tail, is formed by solar radiation pressure and the solar wind pushing the gas and dust directly away from the sun. So the tail always points away.
Makes sense.
But with 3I ATLAS, particularly in some early observations, what we saw was this broad fan-shaped coma of gas and dust, but with a distinct brightening, a concentration of material apparently on the side facing the sun.
Pointing towards the sun instead of away. I can see why that fueled some of the early wilder speculation about, artificial propulsion or something.
Exactly, it looked counterintuitive. But if we apply Occam's razor here, the principle that the simplest explanation is often the correct one.
There's probably a natural cause.
The most logical natural explanation is simply that the sun-facing side of the comet's nucleus is receiving the vast bulk of the incoming solar energy. It's getting cooked directly.
So it's just outgassing much more fiercely on that hot side.
Far more vigorously than the shadowed, cold, dark side. So what you're seeing isn't really an anti-tail pointing sunward, but rather a highly focused ejection of gas and dust coming off the sunlit hemisphere due to that intense, direct solar heating.
Okay, that makes more physical sense. Did other telescopes confirm this?
Yes, the Hubble Space Telescope observations really nailed this down. The detailed paper analyzing the Hubble data explicitly stated, and I'm paraphrasing slightly here, that the object was clearly active at 3.8 astronomical units pre-perihelion, so still quite far out, showing dust emitted predominantly from the hot sun-facing side of the nucleus.
So Hubble saw the same thing. Case closed on the anti-tail mystery, pretty much.
Pretty much. And the key insight from that Hubble data, connecting back to the chemistry, is that this extreme activity at such a great distance appears to be directly attributable to its highly exotic composition compared to our typical solar system comets.
And that composition differences.
It's characterized by that massive abundance of carbon dioxide ice we talked about earlier,
Yeah.
CO2.
Right, the stuff that sublimates relatively easily compared to water. That high CO2 ratio must be really significant then. What does that tell us about where it might have formed?
Hubble data allowed the team to estimate the CO2 to water ice ratio at an extraordinary 8-to-1, maybe even higher.
8 times more CO2 ice than water ice. Wow, how does that compare to our comets?
It's almost reversed. Homegrown comets that we've studied up close usually have ratios where water ice is overwhelmingly dominant. This incredibly high CO2 ratio strongly indicates that 3I ATLAS likely formed much, much further away from its parent star, or perhaps in a significantly colder region of its original protoplanetary disk than where our own comets formed.
Colder formation means more CO2 could freeze out and get incorporated.
Exactly. It implies a formation environment, a birth condition, that we haven't typically seen reflected in comets from our own Oort cloud or Kuiper belt. It's another piece of evidence pointing to its truly alien origins.
And this high CO2 abundance, this easily sublimating ice, that must be the engine driving the massive mass loss, right? Which then explains why the comet shattered all the predictions for how bright it should get.
That's the connection. The models, based on typical comets, predicted maybe a 1.5-fold brightness increase over a certain period as it approached the sun. Instead, 3I ATLAS brightened by a factor of 5, maybe more. It flared up dramatically.
Well, 5 times brighter than expected. Why?
That exponential brightening is almost entirely due to the absolutely huge volume of fine dust being ejected, carried along with that sublimating CO2 gas. The Hubble team calculated the dust loss right. It's staggering. At a conservative minimum, they estimated 12 kilograms per second.
12 kilos of dust flying off every second.
That's the low end. It could potentially have peaked closer to 120 kilograms per second during its most active phases.
Okay, let's just pause and put that into context for you listening.
Yeah.
Take that high-end estimate, 120 kilograms every single second. If you calculate that out over just 1 hour, 3I ATLAS could be ejecting over 430 metric tons. That's 432,000 kilograms of material into space every single hour. Persistently. That is just a mind-boggling amount of mass loss.
It's a phenomenal rate of shedding material. It's essentially creating this enormous expanding dust cloud around itself. And that cloud is the core of the brightness puzzle solution.
How does the cloud make it so bright?
This huge cloud is composed of extremely fine, reflective dust particles. Think of smoke or fog, but on a cosmic scale. This cloud dramatically increases the object's overall albedo.
Albedo meaning reflectivity.
Exactly, its ability to reflect sunlight. If you wear a black shirt versus a white shirt out in the sun, the white shirt reflects much more light and looks brighter. This dust cloud acts like a giant white reflective shroud wrapped around the actual nucleus.
So it scatters way more sunlight back towards us.
Much, much more sunlight than the dark, relatively small nucleus could alone. That high albedo from the dust cloud causes it to appear dazzlingly brighter in our telescopes. And we know the nucleus itself is substantial enough to support this. The estimates put the solid nucleus at about 2.8 kilometers in radius, so about 3.4 miles across. It's a decent size, certainly large enough to hold, and then shed this immense volume of dusty CO2-rich material.
Wow. Okay, the sheer complexity of just what we've discussed so far, the exotic chemistry, the nickel carbonyl, the CO2 ratio, the explosive mass loss, the confusing naming conventions, even it really highlights a crucial point, I think. Which is that following a story like this, where the data is moving faster than peer-reviewed science journals can even publish sometimes, it's a genuine challenge in this information age we live in.
It absolutely is. That's the information deluge right there. You're trying to synthesize data points coming in from astronomers in Chile one day, maybe a preprint paper posted on Archive the next, mixed in with sensational headlines screaming about fleets or anti-tales. It's tough.
It really is, and that's exactly why I personally rely on tools that help cut through that noise, that help me make sense of it all. I just want to take a quick moment here to talk about ground news, which genuinely helps me navigate this kind of information overload daily. I was just looking at articles about this race to observe 3i ATLAS through the platform earlier today, and one of the features I find incredibly useful is the ability to set up personalized categories. So I track specific scientific topics like asteroid updates or new comet discoveries, but I also use it for complex global events that require synthesis, like international conflicts or major economic shifts.
But filtering helps focus things.
It does. But the feature that, for me, makes ground news really revolutionary is the bias assessment tool.
The spectrum display.
Exactly. If I look at a story about, say, space exploration policy or funding for planetary defense, ground news immediately shows me the political bias of the different sources covering it. Is this article leaning left? Is it leaning right? Or is it coming from a more independent source? And critically, it also assesses the factuality rating of those sources.
Yeah, when you're dealing with contentious issues, whether it's in science policy or geopolitics or anything else really, being able to see that spectrum of coverage, that synthesis, is just invaluable.
It really is. You can look at how the story is being framed by left-leaning media, how it's being framed by right-leaning media, maybe compare that to centrist or independent reporting, and then you can synthesize the, hopefully, center truth yourself. You're not just stuck relying on one tribal viewpoint.
It encourages that critical comparison.
That ability to look beyond the partisan constraints and find the synthesis, that's what makes this platform so powerful, I think, especially for the kind of discerning listener we have. So if you are interested in following along with some of these sourced articles we mentioned and also supporting this deep dive, Ground News is offering a special deal right now. You can get a month's subscription for just a small fee, and it's 40% off the regular annual price if you decide to stick with it. Just check out the link in the description. It genuinely allows you to follow the complex trail of breadcrumbs we discuss here, and frankly, it helps us continue to deliver this kind of high-level analysis.
Absolutely. Okay, so with that necessary context on navigating the infosphere established, let's return to 3i ATLAS itself and this frantic scientific race to observe an interstellar ghost, because time is really of the essence here.
Right. And the primary challenge, as you mentioned, remains this observational handicap. The comet is moving so incredibly fast and on such a trajectory that it will reach perihelion, that's its closest approach to the sun, when it is almost directly on the opposite side of the sun relative to Earth.
Bad timing for us.
Terrible timing. That geometry makes detailed Earth-based observation or even observation from near-Earth telescopes like Hubble or Webb virtually impossible right during its peak activity period when it's likely outgassing the most.
And compounding that challenge is its actual motion through the solar system. As we touched on, it is traveling on a retrograde high-speed orbit.
Okay, let's break down retrograde again.
Retrograde motion simply means it is moving backward, essentially east to west through our sky, against the overall flow of our entire solar system. Almost everything in our solar system, planets, asteroids, most comets, orbits the sun in a counterclockwise direction if you look down from above the North Pole.
Right, we all go the same way around.
Pretty much. But 3i ATLAS is going the opposite way. It's bucking the trend. And this backward motion is one of the strongest kinematic indicators, one of the best clues from its movement alone, that the object originated far outside our solar system. It didn't form with the rest of us.
It's the ultimate sign of being a non-native traveler crashing the party from the wrong direction. And its velocity is just staggering, isn't it?
It really is. Its speed at perihelion when it's closest to the sun and moving fastest is estimated to be around 68 kilometers per second relative to the sun.
68 kilometers per second, that's hard to even conceptualize.
Incredibly fast. And that speed, combined with its retrograde, head-on trajectory relative to the planets, means that the window for any spacecraft to potentially capture useful data as it zips through the inner system is incredibly brief.
Right. If we use that two-lane highway analogy again, where we, the solar system, are traffic moving one way, and the comet is a car speeding head-on in the wrong lane,
the closing speed is immense. The encounter is over in a flash. It ensures that any opportunity to observe it up close, or even from a moderate distance, is vanishingly small and requires perfect timing.
And because of this extraordinary nature, its speed, its origin, its weird chemistry, there was that paper you mentioned, 3i ATLAS, direct spacecraft exploration. That made a really powerful case for prioritizing it, didn't it? Suggesting it might be something truly ancient.
Yes, that paper put forward a really exciting hypothesis. It suggested that this object, 3i ATLAS, might actually be a relic from the galaxy's cosmic noon.
Cosmic noon? What's that?
Cosmic noon refers to the period in the early universe, roughly between 9 to 13 billion years ago, when star formation throughout the cosmos was at its absolute peak. The galaxy was churning out stars at a much, much higher rate than it is today.
Okay, so this comet could be from that era.
That's the tantalizing possibility. If 3i ATLAS originally formed way back then during cosmic noon and was ejected from its young star system shortly after, it potentially offers us a pristine, almost perfectly preserved sample of the raw material, the plantesimals, from that specific ancient epoch of galactic history.
Wow, so it's like a time capsule from when the galaxy was young and hyperactive.
Exactly. This object could literally reveal the fundamental composition of planetary building blocks during a period when the galaxy was forming stars like crazy. It's essentially a piece of primordial history, frozen and delivered right to our doorstep, potentially far more accessible than trying to directly probe a star system billions of light years away and billions of years in the past.
Okay, so the stakes are incredibly high scientifically, which means we have to leverage every available spacecraft we possibly can, even if the chances are slim. What are those long-shot observational opportunities?
Well, the paper outlines some specific orbital alignments, potential brief windows where existing spacecraft might get a look, depending on their own trajectories and instrument capabilities. The Psyche mission, which is on its way to the asteroid belt, had a potential, though probably difficult, window back around early October.
Okay. Any others?
Missions already stationed out in the solar system, like the HiRISE camera on the Mars Reconnaissance Orbiter, the Lucy mission, which is currently flying toward Jupiter's Trojan asteroids, and maybe the European Space Agency's Hera mission. They might have had potential viewing slots around mid-October.
Further out,
the Europa Clipper mission heading to Jupiter and the ACES JUICE mission also exploring Jupiter might get chances in late October or early November, depending on the comet's path and their own positions.
And what about for us here on Earth? When do we get our best chance, even if it's past its prime activity?
Our best, albeit probably somewhat faded, opportunity from Earth or near Earth orbit will likely come around December 19th. By then, it should have pulled far enough away from the sun in our sky to be potentially visible again in the pre-dawn or post-dusk sky, though it will be much fainter.
So a lot of long shots, very tight windows, but you mentioned one particularly exciting possibility involving an existing mission.
Yes, perhaps the single most exciting serendipitous possibility involves NASA's Juno mission.
Juno! That's orbiting Jupiter right now, isn't it?
Exactly. Juno is currently in a long looping orbit around Jupiter. And due to the precise trajectory calculated for 3I ATLAS as it swings through the solar system, Juno is predicted to pass directly through the extended cometary tail of 3I ATLAS.
Whoa! It's gonna fly right through the comet's wake. That's incredible luck. An accidental intercept.
It is an unbelievable stroke of scientific good fortune if the predictions hold. It would be a scientific bounty.
What could Juno find by flying through the tail?
Passing through the tail, even the tenuous outer parts, would allow Juno's instruments, which are designed to study Jupiter's magnetosphere and particles, to directly sample the ejected gas and dust from an interstellar comet. The nickel, the CO2, the water vapor, the dust grains, it could provide definitive in situ measurements.
Right there, sampling the actual stuff.
Exactly. It could confirm or fundamentally challenge all the chemical theories we've been discussing based on remote observations. We honestly couldn't ask for a better, albeit unplanned, chance to directly examine material from another star system. Fingers crossed for Juno.
Absolutely. And speaking of spacecraft encounters, you mentioned the Psyche mission earlier, the one that might have gotten a quick look at the comet. Its primary target, the asteroid 16 Psyche, is actually highly relevant to this whole conversation about cosmic resources and our future in space, isn't it?
Very relevant. 16 Psyche is a fascinating object in its own right. It's a massive asteroid, resides in the main asteroid belt between Mars and Jupiter, and it appears to be extremely metal-rich.
Metal-rich how?
The prevailing theory is that Psyche is actually the exposed remnant core of an early protoplanet or large planetesimal that got destroyed billions of years ago, maybe through ancient collisions. Its outer rocky layers were stripped away, leaving behind mostly the dense metallic core.
So it's essentially a free-floating early planetary core made mostly of nickel and iron.
That's the hypothesis the Psyche mission aims to test. It's equipped with multispectral imagers, magnetometers, gamma ray, and neutron spectrometers to map its surface and determine its composition precisely.
And the potential economic implications of an object like Psyche, well, they're astronomical, literally.
They are almost impossible to truly comprehend. The estimated value of the metals contained within that single asteroid, primarily iron and nickel, but likely also including significant amounts of precious metals like gold and platinum, is often quoted at figures like $10,000 quadrillion.
Okay, let's just process that number. That's a 1 followed by 19 zeros. It's vastly larger than the entire current global economy.
By many orders of magnitude. And that staggering number, while maybe theoretical for now, really underscores the long-term economic imperative behind what some call the call for a spacefaring civilization.
Right. This is where the really long-term vision has to kick in, doesn't it? We as a species are currently confined to a single planet with demonstrably finite resources. And so much of our terrestrial conflict, geopolitical tensions, resource wars, economic competition, is fundamentally driven by a scarcity model. The belief that we must fight over dwindling reserves of minerals, energy, even land.
That's been the paradigm for human history.
But if, and it's a big if we achieve a truly spacefaring civilization, one capable of routinely accessing and beginning to harvest the effectively infinite resources contained just in our own solar system's asteroid belt, let alone beyond.
You fundamentally change the economic equation.
Exactly. You potentially pull the rug out from under scarcity-driven geopolitics entirely. If resources like metals, water, energy become effectively post-scarcity, sourced from space, what does that do to the drivers of conflict on Earth? It's a profound thought.
And we have to recognize the deep, perhaps hopeful, irony here. The very technologies that we need to achieve this leap into space, things like advanced rocketry, precision robotics, complex orbital mechanics, autonomous systems.
They're the same technologies developed for planetary defense and, historically, for warfare.
Precisely. The tools are often dual use.
Which makes the whole planetary defense context we discussed earlier inextricably linked to this future of resource utilization. You mentioned the DART mission, the Double Asteroid Redirection Test.
Right, NASA's successful mission in 2022.
DART proved for the first time that we humans can physically alter the trajectory of a celestial object, even a small asteroid moonlet. That capability is absolutely crucial for protecting Earth from potential impact threats.
Defending the planet.
But that same capability, that ability to nudge an asteroid, is also the foundational technology for the future possibility of gently nudging a resource-rich asteroid, like a smaller version of Psyche perhaps, into a more accessible orbit for potential mining or processing.
It's the same toolkit.
It really is. We are literally learning how to turn the potential swords of planetary defense technology into the plowshares of future cosmic resource harvesting. It's a powerful convergence.
That's a great way to frame it. Now, before we wrap things up with a look at the other spectacular comet coming our way soon, let's just quickly clear up any lingering confusion regarding the crowded skies and this idea of a galactic pinball machine we live in.
Yes, good point. Because the names can be confusing. We need to emphatically reiterate for everyone listening. 3I ATLAS is the confirmed interstellar object, the alien visitor.
The one with the weird nickel signature and the CO2?
Exactly. Now, the other celestial belle of the ball right now, the one getting a lot of buzz for potential naked eye visibility later this year, is Comet C 2023 A3. Suchinshan ATLS.
A different comet entirely.
Completely different. While it might turn out to be spectacular, Suchinshan ATLS is a homegrown comet, likely originating from our own Oort cloud. It is not interstellar. They are totally unrelated objects.
They just happen to share the ATLS designation in their name because they were both discovered by the same survey system, the Asteroid Terrestrial Impact Last Alert System.
Right, so don't get confused by the names. Same applies to other recent comets like A6 Lemon or G3 ATLS. The latter is only related by the Discovery Survey name again. They are all distinct objects on different paths.
And once we transition our views slightly from these relatively rare large comets to the much more numerous near-Earth objects, or NEOs, which are defined primarily as asteroids whose orbits bring them into Earth's general neighborhood, well, the density of traffic becomes frankly alarming.
Yeah, if you've ever seen those visualizations, those animations of the known NEO orbits.
It's an almost unbelievable web. A chaotic mesh of crisscrossing orbital lines filling the space between the planets. It really drives home the point that we live in what can only be described as a cosmic blizzard, or as you put it, a galactic pinball machine.
It's a graphic reminder that we are absolutely not alone out here, even within our own solar system. We are constantly being buzzed by rocks of all sizes.
And our awareness of this swarming traffic, our ability to even see it, has grown exponentially just in the last 50 years or so. The historical census numbers are staggering if you think about it.
What are we talking about?
Back in 1970, astronomers knew of only about 30 NEOs in total. 30 objects whose orbits cross near Earth's.
Okay, 30. Seems manageable.
By 1990, thanks to better surveys, that number had climbed to about 135 known EOs.
Still not huge.
But today, the current estimate, the number of cataloged known near-Earth objects, stands at over 30,000.
30,000, wow. That's a lot more traffic.
It's an enormous increase in awareness. And remember, that's just the ones we've found and cataloged so far, generally the larger ones. There are vastly more smaller ones out there that we haven't tracked yet.
And this growing census, this awareness of 30,000 plus neighbors, really highlights the implications of close encounters, doesn't it? Which, surprisingly, are quite common. You mentioned earlier an object passes within 0.2 AU, which is about 18.6 million miles, roughly once a month on average.
That's right. Close passes, astronomically speaking, happen all the time. Now, the immediate worry is always a direct impact on Earth, obviously.
Right, the extinction level event scenario.
Which is a valid concern, though statistically rare for large objects. But there's another, perhaps more insidious and potentially more frequent problem they need to consider, the overlooked scenario of a significant lunar impact, an impact on the moon.
Hitting the moon instead of Earth, why is that a big deal for us?
Imagine a substantial asteroid, Maybe not dinosaur killer size, but even something relatively small, say the size of that recent object 2024 YR4, that had a small chance of hitting the moon. Imagine something like that impacting the moon's surface at high speed.
Okay, big crater, lots of dust.
A massive high-speed debris shower.
Yeah.
Huge amounts of lunar rock and dust, what we call ejecta, would be blasted violently outward from the impact site on the moon's surface.
And that debris, it wouldn't all just fall back to the moon.
Not necessarily. Because the moon has much weaker gravity than Earth, a significant portion of that high-velocity ejecta could easily escape the moon's gravitational pull entirely and spray out into Earth-Moon space. It could rain down into Earth's orbit.
Ah, so we get hit by moon rocks instead.
Exactly. Now, that debris raining down probably wouldn't cause significant damage on the ground unless it was a truly enormous lunar impact. But think about what orbits the Earth.
Satellites, thousands of them.
Precisely. That high-speed debris field from a lunar impact could easily sweep through Earth orbit and effectively sandblast, damage, or completely knock out huge swaths of our vital satellite constellation.
Wow. Taking out GPS?
GPS, communications networks, weather tracking satellites, crucial defense and intelligence gathering networks, all potentially vulnerable. It could trigger a catastrophic, high-speed space junk cascade event, originating not from Earth, but from the moon.
That's a really scary thought, a neglected category of natural disaster almost.
It really is. It's a plausible scenario that's largely overlooked in current natural disaster planning and satellite infrastructure protection. The crowded skies mean the stakes are higher everywhere in our immediate cosmic neighborhood, not just from direct hits on Earth.
That is a sobering thought on planetary defense to keep in mind. And it brings us full circle, perhaps, back to the other major visitor we mentioned, C-2023-A3, Tsuchinshan ATLAS. While it's not interstellar and hopefully poses no threat, it still promises to be potentially a really spectacular sight later this year, right?
It absolutely does. It has the potential, based on current projections, to become quite bright. It might even produce a noticeable meteor shower associated with its dust trail.
Oh, really? When should people look for that?
Earth is currently scheduled to cross through the orbital plane of Tsuchinshan ATLAS, where its dust is likely concentrated, around October 5th or so. That would be the prime time for dedicated meteor watchers, especially in the southern hemisphere, I believe, to keep an eye out for potential meteors radiating from a specific point in the sky.
Okay, early October for potential meteors. And when will the comet itself be closest and brightest for general viewing?
Its closest approach to Earth, what we call perigee, is predicted to be around October 19th or 20th. Now, close is relative. It will still be a very safe distance away, but that should be when it appears brightest in our sky, potentially even visible to the naked eye if you're under very dark, clear skies, away from city lights.
Something for people to look forward to, hopefully.
Definitely. Though, as experienced comet observers always caution, comets are notoriously fickle beasts. They can be unpredictable. They can brighten dramatically, like 3i Atlas did, or they can fizzle out. They can even disintegrate unexpectedly as they round the sun and face the intense heat and gravitational stress. We always have to remember the Tunguska event back in 1908.
The one that flattened thousands of square kilometers of forest in Siberia?
That's the one. While the exact cause is still debated, a leading theory is that it was caused by the airburst explosion, the fragmentation of a piece of a disintegrating comet nucleus, maybe a fragment of comet Encke. It didn't even hit the ground, but the atmospheric explosion was devastating.
Reminder of their power.
Exactly. So we watch these celestial visitors with awe and excitement, absolutely, but also with a healthy respect for their unpredictable nature and potential power.
Well said. As we wrap up this deep dive today, our core mission here really remains the same. We aim to be an antidote, hopefully, to the often shallow, fragmented, maybe even TikTok brain information environment we're all swimming in. We really want to encourage the mental discipline, the satisfaction that comes from following a complex train of thought, from connecting the dots between seemingly disparate fields like cometary chemistry, galactic history, orbital kinematics, even future geopolitics, and resource utilization.
That synthesis is where the real understanding happens.
Exactly. Critical thinking, we believe, thrives when we can follow these intricate relationships wrestle with the evidence, and appreciate the nuance.
And perhaps the most profound realization, the biggest takeaway stemming from this particular deep dive into 3I ATLAS and its cosmic context, is the sheer frequency with which we are now encountering these interstellar visitors.
It really is remarkable, isn't it? We have now had 3 confirmed interstellar objects pass through our solar system in less than a single decade. Oumuamua in 2017, 2I Borsov in 2019, and now 3I ATLAS.
3 confirmed, and as our detection capabilities continue to improve with new telescopes and surveys coming online, we are undoubtedly going to discover many, many more in the coming years. It seems interstellar space is busier than we thought.
And that leads us to the final provocative thought we want to leave you with today. If we have suddenly detected 3 of these objects in such a short period, what does that really imply?
It strongly suggests, doesn't it, that these interstellar visitors, fragments from other star systems carrying alien chemistry, have likely been passing through our cosmic neighborhood all along for billions of years. We just didn't have instruments sensitive enough or surveys comprehensive enough to notice them until very, very recently.
So the profound implication is what? That the future of exploration, the future of understanding our place in the galaxy, might not just involve sending probes out to distant stars, a journey that takes millennia.
Perhaps not exclusively. It might also involve rendezvousing with, capturing, or even just closely studying these objects that have conveniently traveled here to us, delivered right to our doorstep from potentially completely different star systems.
Wow, like cosmic messages in a bottle washing ashore?
Precisely. Each one could provide unparalleled, pristine knowledge about the galaxy's history, the diversity of planetary formation, and maybe, just maybe, eventually reveal the existence of other planetary arrangements out there capable of supporting complexity, perhaps even sentient life. The answers might be coming to us.
That is a truly mind-bending thought to end on. Thank you for joining us on this extensive journey today, diving deep into the science, the mystery, and the sheer spectacle of this current cometary convergence.
It's been fascinating to explore.
We hope you found it valuable. We will see you on the next deep dive.